first one. I think he hasn't given his comment yet. Yes, Patrick, go ahead.
The minimum has to be there.
It has to be there. Why is that?
Because if you go to minimum span tree on the left side and minimum span tree right side, I mean, they touch all first, and then, I mean, it's not like it creates a path or a cycle, it's just connecting two verses together.
I think just going back to previous classes where we said the optimal solution will always have a subset of the optimal solution. If you take that same theory and just kind of expand it onto this, if we're looking for the minimum, the smallest number should always be in that final minimum spanning tree.
Anybody else?
Well, it seems like from the priority queue perspective, if you're using priority queue, you're always adding either one or multiple edges to
hang
the
on,
queue
hang
at
on.
one time.
Wait, where are you?
Oh, you're there.
No, I mean, I could be there or here, but I'm saying that shouldn't change. I'm just simply pointing out that my implementation method should not change a structural question I'm asking.
Sure.
My how question should not change my what answer. So, anybody else on that? So, I think Patrick said probably most, not just clearly, but I think he's most convinced that the minimum has to be there. Can you say that again, and maybe if we can convince everybody else, or we give up, or so? Can you say that why? Sorry, can you say that again? Why does the minimum one have to be there?
I just said it has to be there because you did a minimum span tree on the left graph and then minimum span tree on the right graph. I mean, they touch all first. Since we're not creating a path or a cycle, I mean, we just have to connect the two graphs together with a short step or short step.
Sure is, but to that I can give this contrary view that maybe you don't. I mean, that kind of depends upon your methodology that you built the minimum spanning tree on the left or minimum spanning tree on the right. Maybe I'm just going haphazard way, and I don't have a minimum spanning tree on the left hand side or on the right hand side. Maybe I have one, but I can still try to answer this question in general. So maybe a different way to answer the same question would be to say that, let's say finally, when we have a minimum spanning tree, we do have to have one edge from that set, at least one. We may have more than one, but we have to have one of those edges. If we have none of those edges, that means we do not have all the edges and all the vertices are not connected. The left hand side is not connected to the right hand side. Right? So let's say that some other edges in the minimum spanning tree, in a minimum spanning tree. Let's say this one is here. Then could I not switch this one to my E1 and come up with an even smaller minimum spanning tree, which would violate the example or the assumption of the other tree being the minimum spanning tree? So the first one is definitely true. So if you, and essentially, this goes back to Josh, maybe that this is essentially what we are doing in this algorithm at all. Because what this algorithm, even though we covered it earlier, but it's difficult to see the same thing here. That's exactly what we did in the very first step. What the Prim's algorithm does is, let's walk through it again. So you start with a vertex R to be the root, and just randomly pick, and then you assign, you see which of the vertices are the closest to my current set, and then pick that. That's essentially exactly what you just did. You just said one, and everything else, there's no reason that the left-hand side and right-hand side have to have more than one, right? So in the left-hand side, you have exactly one node, and you pick all the other edges, and you pick the minimum one. So this essentially, this entire algorithm is based on this observation, that if you have a cut, then the minimum edge is going to be there. Just the implementation looks a little different. It's talking about Q and whatnot, but the observation is exactly that. So we start with one, we insert all these vertices, and this is exactly what we do. We pick the next vertex, which we don't have yet, which is the smallest, which has the smallest label. And the label, essentially, we are translating these edge weights to the labels on the vertices. So left-hand side part is a part of the tree that we're growing, and we always pick an edge from here, whatever is the minimum one, except in the algorithm, we don't refer to it as edges, we refer to it as labels on these vertices. We pick the one, we bring it over to the left-hand side, and now we have one more vertex on the left-hand side, the tree, the part for which we already have a tree. And we don't have a tree for the right-hand side, but we keep bringing one node over from the right-hand side to the left-hand side. So this can be one way to articulate Prim's algorithm. And this is at least the book version of how the book says it. It says that you start with the vertex, set its distance to be 0 because you already have that in the set, and give its parent to be null because it's you're trying to create a tree, so that's just a root node. For all the other vertices, set its distance to infinity, and then put them in a queue. Use the distance as keys, and even though this part is essentially up to you on what's the data structure that you want to use, and we will consider both of them, a few of them here. And then you pick the next vertex that has the smallest one, that has the smallest label, bring it over to the left-hand side, and update the vertex weights which are connected to that. So for example, if you bring this vertex over to the left-hand side, then all the edges that it's connected to will become the edges of the cut. So if they have a label here, then maybe now the label of that vertex can change because you now just brought this vertex from the right-hand side to the left-hand side. So if this vertex had some weight, had some label, now this might actually go down. So let's say if this vertex had a label of 8, because let's say there was an edge with a weight 8 here, and let's say this edge has a vertex of this edge has a weight of 4. Once you bring this vertex on the left-hand side, then this label of this vertex is going to change from 8 to 4. Right. So you're keeping an eye on all the vertices that are connected to your set, and you have their label as what is the edge of the smallest, or what's the weight of the smallest edge, the least cost edge that's connected to that vertex from the left-hand side. So is the algorithm clear? Any question on the algorithm itself? Okay, well let's just walk through the example here. So here's just an example here. We say we start with the node here. Let's say we start with the root node E. These are all the edge weights. So if we start with the root node E, we initialize everything else to be infinity because we haven't made any decisions yet. Once we bring E to the left-hand side, or right-hand side, whichever, then we will say that the weights of the labels of these vertices are going to be C, D, and B is going to be 5, 4, and 5, 4, and 5. B is 4, B is 5, C is 5. Right. And the next step, now we're going to pick the one vertex with the smallest label. A still has a label of infinity because we did not change it. Once we selected E to be the root, A was not connected to E, so we did not change its label. So A still has a label of infinity, and these are all the labels. Then we will pick the one with the smallest label here, which is another way of saying that I will pick the least cost edge from this cut. Right? So that's why I asked this question here. So this is now we are selecting the least cost edge from this cut. And we bring that's of course is 4, the D, and then we bring that to the selected side, and then we change the labels of all the vertices that D is connected to. So it's C, B, and A. So B already had a label of 5, so we will not change it to 6. We'll only decrease the label. But C had a label of 5. Now it will go down to label of 4. And A had a label of infinity. Now it will go down to 2. And then we will pick the smallest label again, which is A, and we'll select that, and so on and so forth. So at each time, we are essentially connecting the smallest cost weight in this, smallest weight edge in this cut set. Right now, the cut set is given by A, D, and E on the left-hand side, and C and B on the right-hand side. Right? So the ones that you have selected are on the left-hand side. So are there any questions about the running of this algorithm itself?